Hi and welcome to this section where we are going to look at the first iterative scheme, and this one here is the fixed point iteration method. Okay, so we will start by saying we consider a function, okay, f of x equals to 0, okay, whose zeros or roots we want to find. We can call this equation 1. We transform. The procedure for the fixed point iteration is that we transform 1 into the form x equal to w of x. Okay, after that we take an arbitrary x naught and then compute a sequence. We take an arbitrary x naught and then we compute a sequence x1, x2, x3, and so on up to perhaps xn, wherever you're going to stop in accordance to your termination criteria. Okay, now this sequence here, we shall compute it recursively from the form, which is going to be written by xn plus 1 equals to phi of xn. Okay, now so this is 3. So now what we have to note is that for this procedure, given this function here f of x equals to 0, there are many ways of writing this form here, x equals to w of x. There are many ways of writing this form. We shall see with some examples in a short while. So however, not all these forms here, not all are going to work in the sense of converging to the solution. Okay, remember these are just approximate solutions. However, we have to get solutions which go near, which approach the true solution. So not all will work in the sense of that not all these forms are going to lead to a scheme here xn equals to phi of xn plus 1 equal to phi of xn, which is going to converge to the solution. Okay, so how are we going to select? Okay, how do we know which form of this leads to us to a sequence here which is convergent? So that is the key thing. How do we get to know, or how do we get to pick the right form of xn equals to w of x, which will lead us to, this sequence here, which is going to lead us to a convergent solution? Well, we have a theorem which is going to help us with that. And how does the theorem go? Okay, the theorem says that let x equal to xi. Okay, I hope I wrote it well. Let x equals to xi be a root of our function f of x equals to 0. Okay, we let I be an interval, okay, which contains the point x equals to xi. Okay, further we are going to let this phi of x be continuous. Now this is also another technical term. I hope you remember this from your calculus, that when is a function continuous. Okay, so I will not go into the details of that. If you have forgotten, you please refer back to your calculus and try to remember what they mean that this function here is continuous on a given interval. So let's say let 5x be continuous in I, okay, where when this 5x is defined by x equals to 5 of x. Okay, which form here is equivalent to f of x equals to 0. Okay, so they have been stating the assumptions. Now this is what we check out for. Then if these conditions here of course have held, the above conditions, then if the absolute value of the first derivative, okay, of phi of x is less than 1 for all values of x taken from the interval, okay, then the sequence which is approximated by xn plus 1 equals to phi of xn for values of n equals to 0, 1, 2 and so on, converges to the root x, okay, to the not x equals xi, we can just say to the root xi, okay, provided, wow, there are many conditions, okay, provided the initial approximation, okay, is chosen in the interval I. Okay, just a recap. Yeah, we have done quite a lot. So we have the root, okay, of our function. We have a given interval which they will give us, which contains that given point or the root, and then we have our function here phi of x, which we have said is continuous on the given interval. So I said you have to remember when is a function continuous or when is it not continuous. Okay, there are many things you can look out for. Remember that from your calculus. Okay, function is continuous if it does not skip any value. Function is continuous if it is defined for all values on that interval. Function is, all of those. Can't go into detail for all of them, but hope you remember some of those. And okay, where this function here phi of x is defined by x equals to phi of x, a form which is equivalent to f of x equals to 0, the one we derived from that function. So then if the first derivative okay, absolute value of the first derivative of phi of x is less than 1 for all values of x, it has to be less than 1 for all values of x taken from that interval. Then the sequence which is approximated by xn plus 1 equals to phi of xn for values of n equals 0, 1 and so on converges to the root xi, provided that it is chosen in I. So why did we come up with this theorem? Not that we came up with this theorem. Why have we used this theorem? We have used this theorem because we have been told, or we shall later on see, that in transforming our form f of x equals to 0 into this form here, there are many ways to do it. However, some are going to be convergent and some will not be convergent. Okay, let us stop being quite abstract and look at an example. Okay, so the example here tells us that we want to find a root. Just a minute. We want to find the real root. Okay, we want to find the real root of the equation x to the power 3, this polynomial equation. Okay, we said we shall keep it simple. We shall just do these either polynomials or transcendental or the transcendental functions. Okay, so we have the root of the equation on the given interval. Let me find the interval. The interval is 0, 1, and it is a closed interval with accuracy. Okay, on the interval 0, 1, I hope you remember from your calculus again the difference between an interval which is written as 0, 1 and the interval which is written as 0, 1, or someone who could write 0, 1. Anyway, the point is, I hope you know the difference when you use either the brackets or when you use the parentheses. Okay, I'm trying to get your mind to remember some of those things that we did, but I don't want to fly off the tangent, so I'm not going to get into terminologies of calculus here. Our interest is to find the real root. We're assuming that we know everything about, closed intervals, open intervals, and continuous functions, and so on. So we want to find the real root of this on that, and they have given us a level of accuracy level which is 10 to the power negative 4. So we shall use a word here, okay, in numeric analysis, which is tolerance. Okay, now step 1 is that to find this root, we are going to find this root, we have our function f of x equals to 0, and then we want to write it in the form x equals to w of x. This is just at the back of our minds. Okay, so one could look at this function and then say, please note that I am not in any way going to exhaust all the forms you can write this. Okay, I'm just giving you the ideas. One could perhaps write it in the form x squared, okay, into x plus 1. We pull out here x squared, we have x plus 1, and then minus 1, and then say this equals to 0. Alright, then with that we could make x squared the subject, and perhaps we say that x squared equals to 1 over x plus 1, for which we have that x equals to 1 over x plus 1 to the power 1/2 square root. Not so? Yes, so we have one form, that one there. Perhaps someone else would have said, no, hey, I want to write it in another form. What other form do I have here? Let me just check it out quickly here. Oh, yeah. Perhaps someone could have just said, hey, let me just write that x cubed equals to 1. If we take this on this side, it becomes negative, and then one would say that therefore x equals to 1 minus x squared to the power 1/3. Okay, so we are going to look at these two forms here. Of course, there are many other forms, but like I said, if we do that, then we shall spend a lot of time here. Just going to give you the idea here. Now, how you can pick the form which is really going to work first time, I am not so sure how you're going to do that, but perhaps if you do a few examples, a number of examples, then it can become quite easy for you to be able to find it out. So lots of things. So now here what we would have to do is that okay, for this form 1, let us call this one here form 1, and then we call this one here form 2. Now for form 1, okay, let us write it this way. For form 1, of course we would write now our sequence here, xn plus 1. We want to write it in this form, phi of xn. That means that we would simply say, where is form 1? Form 1, oh here, this one here. So we would simply say that, hey, we have xn plus 1 equals to 1 over xn plus 1 to the power 1/2. Okay. What about for form 2? For form 2, we would write, it's here, it's just a matter of saying that xn plus 1 equals to 1 minus x squared, xn squared, everything to the power 1/2. So we have form 2, our sequence from form 2, and then our sequence from form 1. Okay. Alright, next you will have to check that for form 1 or for form 2, we would have to check that the first derivative, okay, for all values of x taken from the interval they gave us was 1, 2, that for all values of x taken from this interval, that the absolute value of the first derivative is less than 1. That is what we would need to check. Well, that means that we would have to differentiate this form here, okay, with respect to x, or we would also have to differentiate 1 over x plus 1, this form here, with respect to what? To x. Now, for essence of time, please allow me write down what I saw works, and I will also show you in a bit, okay, why I said that one works. Okay, let us use form 1 here. Okay, so for form 1, okay, form 1, I am going to write this down. Please make sure you check this for any errors. Okay, yeah, I may have made an error here, so you make sure that you also do this actively and not just passively. Okay, so we would like to say that if I differentiate that one there, we are going to have the absolute value of minus 1/2 1 over, okay, this is because negative, okay, alright, okay, I'll have that minus 1 over 2 times 1 over x plus 1 to the power 3 over 2, of course, which we can write as 1/2 absolute value of 1 over x plus 1 to the power 3 over 2. So we would like to check that is this, oh, just a minute, that is this less than 1 for all values of x taken from 1 and 2. Okay, oh, maybe something else, someone would have said that is this continuous, because they told us that this phi of x has to be continuous. Well, I think it has to be continuous because where is it? Yes, on the interval, I suppose it is continuous on the interval 1, 2, because it must be, if you try to visualize it and graph it, you will see that it is continuous. It does not skip any value. It is defined for all values between 1 and 2, even 1 and 2 inclusive, and yes, it does not skip, it does not have any discontinuity, and so on. So I think I can comfortably say that this function here is continuous on 1 2, on the interval 1 2. So if it is continuous on the interval 1 2, then perhaps we'll go ahead and then check for this condition, that is this less than 1 for all values of that. Well, I think one trick that can be used here is to try to find the minimum, its minimum on that interval, or its maximum on that interval. In both cases, you'll find that the minimum on this interval here, I mean the minimum of this function here, perhaps let's see, when x equals to 1, okay, let us look at the endpoints here. When we substitute in x, when we substitute x equals to 1 in here, then we have 1/2, then 1 over 2, then to the power 3 over 2, which is the same as 1/2, then 2 to the power 3, then to the power 1/2, that is 8 to the power 1/2. Okay, so we have 2 root 8. Okay, and then this is when x equals to 1, and then let's see, when we substitute in x equals to 2, what do we have? We have 1/2, then we have did I say x equals to 2? Yes, x equals to 2, then 1 over, what is 2 plus 1, that is 3 to the power 3 over 2, which is going to be 1/2, then 3 to the power 3 is 27, then this is root of 27. Okay, so if this function here, like we said, is continuous, is well behaved, and is, you know, either increasing or it is decreasing, then if, you know, one of these values, end values, gives you this which is less than 1 and this which is less than 1, then I suppose I think we are safe to say that we are sure that this function here is less than 1 for all values of x in that interval. However, the curious person can also try to just do a simple sketch of a graph. Some of these functions may be, I don't know how good we are with our calculus, but some of them may be quite, especially the transcendental, may be quite easy to know on the graph. Maybe the exponential, the logarithmic, the trigonometric, those could be quite easy just to graph and know that maybe they are less than 1 or they are more than 1 in this interval. However, some of these polynomials here may be a little bit tricky, okay, and they may involve you to have some techniques here and there which I may not be able to exhaust, or I may not also have very well on my fingertips. Or however, this is a point for you to note that you have to be sure that this is actually correct. You have to be sure, and also look through your calculus to remember some of these other methods. Okay, so you could also try using some of those same arguments on this other form 2 which we had here, by differentiating it. Okay, of course we differentiate. Okay, that one there, which led us to, which form was it? From, yes, okay, yeah, okay, just a minute. Yeah, I don't see it. Where did I write? Okay, yeah, it is this form here. I think this was confusing me. It is not 1 minus x squared, it is 1 minus x squared to the power 1/3. This is not 1/2, this is 1 over 3, the form 2. Okay, so by differentiating this, okay, and then you make sure that this, when you differentiate it and then you take its absolute value, that is it less than 1 for all values of x taken from the interval 1 2, you can check that out. Okay, if it is, then then perhaps I made an error here on this form. Okay, Okay, let us assume that okay, this is correct and we have done that. So if that is correct, then next we would say that okay, we are going to use that form. So we have the form which we are going to generate our sequence, which is xn equals to 1 over, sorry, this is xn plus 1 equals to 1 over xn plus 1 to the power 3 over 2. Okay, so that is what we are going to generate. So what would one do? We have the interval. Okay, we have the interval given to us is 1 2, okay, on the interval 1 2. So we are going to choose x naught, our initial approximation, from this interval here within here. Okay, so perhaps somebody could choose what should I say, maybe someone could choose something which is in the middle, you know. Maybe you could choose, maybe you could start with 1.5. Is the interval 1 2? Wait a minute, where did I get 1 2? This interval is 0 1. Oh no, oh no, this is not nice. I don't know why. Where did I get confused with? Okay, the interval here is 0 1. Okay, okay, so let's just do this again, where we checked 1 2 for this here, 0 1. Okay, I'm really sorry for that, but let us just substitute in when x is equals to 1. This is okay, it won't change. Okay, so here we can say that now when x equals to 0, so when x equals to 0, what do we have? We have it is 1. Yes, it is 1/2 times 1, because when x equals to 0, this is 0 plus 1, that is 1. 1 divided by 1 is 1, then 1, then the number 1 to the power raised to the n number is still 1, so we have 1/2 times 1. Okay, so we have 1/2 times 1, which still gives us 1/2, which is less than 1. Then all the other arguments have been trying to make still hold. Okay, yeah, so this interval is 0 1. I am really sorry for that. I think now the video is taking quite long, and I hope we can end it soon so that I don't make any more silly mistakes. So this, our initial route here, which I had chosen x equals to 1.5, cannot work because the theorem told us that our initial approximation has to be taken from the interval here. So perhaps we could choose 0.5 because it is between 0 and 1. Okay, that is a good choice for us to start. So you can either do this. If we are going to do it by hand, we shall always try out simple problems by hand. We have here n for our number of iterations, and then we have the value of xn, and then what else do we have to compute? Maybe we have to compute xn plus, and this is not to the power 3 over 2, is it? I think this is to the power 1/2. I hope that is it. I should stop making all these mistakes. Yes, it is x plus 1 to the power 1/2. Okay, good. So next thing we can compute is xn plus 1 to the power 1/2, which is the same as xn plus 1. Then we take the square root, and then lastly we can compute xn plus 1, which is given as 1 over square root xn plus 1, i.e. xn plus 1 to the power 1/2. Okay, so we have that, and then we have that, we have that, and then we have this last computation. Then the rest is for us to fill in. Of course, initially we have 0, and then our xn plus 1, we have picked it as 0.75. okay, then you compute the value here. Let me just copy this. This is 1.3 something, and then 1 divided by square root of 1.3 something, you say 0.75 something. Okay, so then on the next step, of course, now when this is 0, that means that we have x naught, and then we use x naught to compute x1. Okay, now to compute x2 we would use x1. Okay, so that means that here, when on our next iteration, when n is 1, then the x naught, okay, I mean, yes, the x one x what. So we have here this, and then we have just a minute, we have xn plus 1, okay, equals to a function of xn. When n is 0, here, we compute x1, okay. Then when n is 1, we have x2, okay, and then here to compute x2, this value here, to compute x2 here, we shall use the value of x1, and x1 is what we have over here. So we shall just take this value and then we drop it down here. Was it 0.75? Yes, it was 0.75 something. So this is what we write, 0.75 something. Then we compute this value, and then we compute this value, and then this value. Now we use it here to compute this and compute that, and so on until we reach something. Maybe we should have added a column for the errors, okay. In the last column, maybe we have the errors, and the errors are going to be absolute value of xn plus 1 minus xn, okay. And this one here, we compute the value, we compute, and we are trying to ensure that this value here is, if it is less than 10 to the power negative 4, then we stop, okay, we stop, and that will be our root. If not, we can continue on and on and on and on. Okay, now, like you have already seen, the mistakes that I make in computing some of these things are quite many. So our problems, we shall stick to problems which are quite easy for us to compute by hand, okay. Or the others, I will have to ask you to learn how to do them on a computational tool. Like I said, we shall use MATLAB. So for this problem here, I came up with, I just wrote a very simple algorithm, okay. And however, I used Python, okay. I used Python. The language is different. The language is different, meaning the syntax, the way you write some of these commands is of course different, but the logic is the same. The logic is the same. Why I didn't want to do it in MATLAB is because the exercises, I'm giving them to you in MATLAB. So if I do them for you, then it may not be very helpful. So what I just decided to do is just to use Python here, and then yes, you can follow the same logic, just change just the syntax here and there in MATLAB, and perhaps even write better code, okay. If I still insist, please look through in this video and look through all the mistakes, and also look through in the text. Oh, by the way, the text also has lots of mistakes. The text has lots of errors, okay. So please note, please always put those in the comment section, and yeah, that will be helpful. So I'm going to end this quite long video by taking you to the form for which I had written for this, the algorithm for this, okay, because I was so lazy to compute this and then compute this in calculator and then this. So I'll just take you here, okay. So I'll take you to the text editor. I hope you can see that. So this is the Python language, okay. You don't worry about the terminologies here. So what I do import math is just to import the module for which I would, use if I want to maybe find the square root, or okay, this is okay, powers not really, because it is in the standard library. Yeah, so for this case I just wanted to make use of the square root function, which is contained in this math module, and that is why I had to import it. So the rest of the idea follows as follows. The tolerance is 1 times 10 to the power negative 4, and then okay, I can start with 5. We have said we start with 0.5, and then I start with an error which is big. I say that error is 1, okay, because somewhere in the while loop here, okay, I make use of error. So that is why I had to set it up there, because I cannot use what is not yet defined, okay. So I defined an error, and then the tolerance is already given to us. So of course, while we enter the loop here, the error, which is 1, is definitely bigger than the tolerance which we have here. So this loop is going to run at least once, then we will check, then we will compute the error the right way. Okay, so here what do we have? The first form, or the form 1 which we have, remember we said xn plus 1 equals 1 over the square root of xn then plus 1. Okay, so that is what we have here. This is all. This is x1 represents xn plus 1, and then x0 simply represents x0. Okay, then the other form here, the hashtag here means that I just commented it. It's not going to run it, but this was the other form which we ran, which is 1, I think it was 1 minus x to the power, okay, xn plus 1. Oh, this should have been x1. I forgot this. I write the xn plus 1 equals to 1 minus xn to the power 3, then everything to the power half. This was the form 2 which we had. Okay, and then the error, I come here. Okay, this is commented for now, it is not running, but I will just run it later on to show you that one of them worked and the other did not work. Then the error is simply the value of x1 I get minus the value of x0. Okay, then in the next one we set x0, the previous value, okay, to be equal to the previous value. Okay, we use in the next place here, we are setting x0 now to take on the new value. Just if I can go back to the file we had here, where we say it here, you see here, this is x1. Okay, and then we say that now in the next loop we use this value of x1 right here. Okay, in other words, that now the x0, okay, takes on now the previous value, and then we use this to compute the next value, and so on and so on. So if we follow that logic, this is what we write. And then what did I put? Count. Okay, I just put count. I set a count to 0. Why? Then I started counting because I just wanted to know the iteration counts, how many times. So each time the loop runs, it simply updates count. Count was 0 here initially, so it will just, if it runs the first time, it will get count plus 1, which will be 0 plus 1, then it will give us maybe 1. If it runs, it goes and runs the second time, then it will update, because now count is 1, now it will say 1 plus 1, which will give us 2, and so on. So I hope this is fine. Then we can run it here. Remember that you will be using MATLAB. Oh, I should have already done it. No, I'm sorry, the video is already so long. I should have already set this to I should have already set it to the folder where I wanted to run it from. So this is this, and I think it is must be here. Just a minute. Yes, it is here. And then I'll do that, and then I'll do, what did I write? Okay, then okay, just a minute. What name is it? It is fixed point. Okay. Oh, all right. I have to save it, and then we have to go back. Sorry about this. Okay, and then we run it. So I run it, and then it gives us iteration count number 1, number 2, number 3. It gives everything here. How maybe what the output you should know is that it is here. We say the iteration number, then it will put the count, then it will put the root, which is x1. Remember, we are computing x1. X1 is equivalent to xn plus 1. So every time we are computing x1, the root, and then we are computing here the error, which we are getting by x1 minus x0. So that is the output on the screen. So when you also compare it by hand, I think this is the value which is in the notes, okay, and then you should also try it by hand and then you see. So now lastly, I know this is taking so long. Lastly, we would like to see, so this form here is convergent and it has given us, you know, what we want. So lastly, now if we can comment that and remove the comment to that and then save that, and then we try to run this other form which we have, okay, and then we run this other form and then we see. So you can see that this other form which we are running, which I told you that you should check if it is, if you know, the absolute value of that form is less than 1 for all values of x in the interval 0 1. So perhaps you can see that this is most likely going to run forever and ever, because I think it already violates the conditions we have. Okay, so yeah, so we are going to stop here, and I hope this has, yeah, I feel this has been really long, but the next examples are going to be quite short, and then yeah, I hope you understand. Thank you very much and have a good time. Okay, bye bye.